Hello everyone. Welcome to today's video lecture. So in the previous lecture, we have discussed about the quality, quantity, the quality, various physical and chemical characteristics of sewage, the BOD calculation, and the disposal of sewage in mainly urban areas. So in today's lecture, we'll discuss about the conveyance of sewage, how the sewage is finally carried. Okay. So that conveyance is with the help of a conduit called sewer. Sewer helps in the conveyance or the transportation of the sewage or the storm water, whatever you may call it, to the final treatment plant. So they will collect after collection of all the sewerage, okay, or the storm waters uh, from the household. It will carry this sewage in a conduit and bring it to the water treatment plant. So that portion of this conveyance through conduit is the sewer. So there are mainly three types of sewer. Stormwater sewers, they mainly carrying only stormwater. That is all the rainfall that is happening in a catchment will uh, get accumulated in in such sewers. It will contain only rainfall water. Okay, that is called as stormwater sewers. Sanitary sewers are nothing but the sewers that carry all the domestic wastewater and sewerage coming out from the households. Wastewater that is coming out, that is the sanitary sewers. And combined sewers is they will carry both stormwater and sanitary sewers. So in a country like ours in India, we generally opt for combined sewers. But where quality is an issue or treatment for more precise and more genuine treatment of sewage, what we do is we sometimes we separate these two sewers. Okay, so these are based on the type of liquid flowing in it. This sewers is has been the sewer has been classified. So now some basic difference between water supply pipes and sewer pipes. The first difference is water supply pipes will carry pure water containing any kind of solid particles, either organic or inorganic. Okay, without containing, sorry, this the water supply pipes carry pure water without containing any kind of solid particles or either organic or inorganic. So it will contain pure water. The water after the treatment will be carried by the water supply pipes to the um, final household. Okay, pertaining to certain pressure, of course. There is some design pressure for which the water supply pipes are being designed, and at that particular pressure, water is being carried through the water supply pipes. But in case of sewer pipes, on the other hand, does not contain particles in suspension, which might settle down and cause clogging. Okay, so what happens is the sewer is not just a liquid. It will contain your solid particle, grit, and other urine, stool, and other waste particles. So you will have small solid particles also. What happens is solid particles for some time it will be in suspension. And after a particular time, if it is allowed to stagnate, it will settle down. When the solid particles settle down in the sewer pipe, it it will clog the pipe. It will cause obstruction to the flow. Okay. So how this can be prevented? The sewers should be laid at such a gradient or at such a slope so that it will develop self-cleansing velocity. Means the sewer pipe should be laid at such a slope, such a minimum slope in the ground that it will automatically develop that velocity which will self-clean all the solid particles that is being deposited in the sewer. So such velocity is called self-cleansing velocity. That will, of course, we'll study in the next topics. The next difference is the water supply pipes carry water under pressure. Okay, this is already discussed. They will always water supply. You cannot carry water supply under gravity because sometimes water has to be supplied because this water has to be supplied to higher elevation. So in order to supply the water from a place of lower elevation to higher elevation, this has to have a certain pressure head, and that pressure head amounting to rho gh, that pressure head that much pressure head will make that water rise vertically. So it is very important that for that the water will flow full. But in case of sewage, of course, there is no pressure flow. There is always a gravity flow. The sewers are laid at a particular slope, and uh, the sewage is made to flow under gravity. Third important difference is the water supply pipes flow full because they have to develop pressure. Water flows under pressure, whereas in case of sewers, they flow partially full with certain freeboard erupted based on their discharge capacities. So what is freeboard? Freeboard is when the sewer is flowing, the sewer cannot flow full. Okay, you have to keep certain space because uh, you do not know. In case of sewers, what happens is you do not know the amount of solid impurity, solid particles that is coming. Okay, it does not only contain the liquid part. First thing. Second is sometimes unprecedented or some infiltration of water from the ground also comes into the infiltrated water also comes in, enters the sewer. In that case, something that we have not anticipated, some unanticipated flows occur. Sometimes does. Sometimes there is, uh, sudden increase in population or demand, and due to which there will be sudden increase in sewage production, of course. But your sewers are not designed for that capacity. So, in order to refrain from such conditions, we generally keep a certain space available over the full supply level of sewer. Okay, that space from the top of the sewer to that FSL, to that full supply level, is the freeboard. So that freeboard you have to adopt, and that is based on the discharge capacities. The more the discharge, more will be the freeboard. So you have been, there's a table for certain discharge. This is the freeboard. Generally, minimum freeboard of 0.3 meter is adopted everywhere for sewers. Okay. So now let us get to the hydraulic design. How the sewers are designed hydraulically. Okay. So certain formulas are there. Chase's formula. Okay. V equal to C square root of R into S, where R is what? A by P. A is the weighted area. P is the weighted perimeter. Okay. So this will give you know R, but S is the longitudinal slope. C is Chase's constant. So that is one constant that you can calculate using this formula, which is called as Cutter's formula, given by C is equal to 23 plus 0.00155 by S whole by 1 plus 23 plus 0.00155 by S into N by square root of R. Okay. Using this formula, if you do not know the value of C, you can calculate. If you know N, if you know R, you can find what is C, and you put C, you know R, you know S, you can find what is the velocity. So this is using Chase's formula. For Manning's formula, this is the generally most used formula for uniform flow. So this is given as V equal to 1 by N, R to the power 2 by 3, S to the power half. Or R is the, again, R is the hydraulic mean depth, S is the longitudinal slope or hydraulic gradient, N is your Manning's constant. So this Manning's constant is also called as roughness coefficient. So this depends on the roughness of the material of sewer used. For cement concrete sewers, for earth, your vitrified tiles sewer, for brick lining sewer, for different material of lining, value of N will be different. Okay, more rougher the surface, rougher N, higher will be the value of N. Generally it varies from 0.01 to 0.04. So this is the range for your N. Now, in case of water supply pipes, we use William Hazen formula, that is given by B equal to 0.85 CH R to the power 0.63 into S to the power 0.54. So if you know R, if you know S, again CH is a constant. For cast iron pipes, for water iron pipes, CH is 130, and for other pipes it is 100. So this value will be known to you depending on the material. You can write what is the velocity of water supply pipes, water in water supply pipes. Okay. So these are certain formulas, mathematical formulas or empirical formulas, you can say, based on which the hydraulic design of sphere is done. Again, we have discussed in the previous topic that about self-cleansing velocities. So what happens when the sewer enters the when the sewage enters the sewer, it is flowing under the gravity. Okay, so So now again, as we know that the sewer contains solid particles, inorganic, organic, grit, okay, sand, anything. Along with the sewage, liquid sewage, it also contains solid particles. The solid particles, again, when it is allowed to stand, and the velocity is very low in the sewer. If the slope is very less and the velocity is very low, okay, at that time it is almost a standstill kind of a condition for the flowing sewer. So in that case, what happens is your settling the particles in suspension will start settling at the bottom of the sewer. So it will reduce the capacity. Okay, if it reduces the capacity, flow will reduce. Okay, discharge capacities will be reduced. So in that case, we have to develop a certain velocity which is called a self-cleansing velocity, and it will be developed automatically if you lay the sewer at a particular slope. If the gradient is higher, always, from Manning's formula you can see, here velocity depends on the slope. Greater the slope, greater will be the velocity. So at a particular, if you increase the slope, your velocity will increase, and this particular velocity, which is given as self-cleansing, it will clear all the particles that have settled down, and it will prevent the clogging. So this is necessary in case of sewer. One is self-cleansing velocity and another is the non-scouring velocity. That is, this puts a limit to your maximum velocity in a sewer and a minimum velocity. So as per formula, you can calculate the self-cleansing velocity as 8g f dashed k d dashed g minus 1 square root. Okay, square root of enter the square root of entire square root of under root 8g by f dash k d dash g minus 1, where g is your acceleration due to gravity, f dash is the friction coefficients, Darcy's friction coefficient, k is maybe 0.0032, 0.01, whatever value, k is a constant, d is the grain size, okay, g is the uh, uh, specific gravity of the solid grains, okay. So as per, if you put all this formula for a particular grain of 1 mm, you can find the self-cleansing velocity as 0.545 meter per second. And average velocity developed in sewer is 0.9 meter per second. So now there is a table, of sewers that we have provided for what is the non-scouring velocity, what is the minimum velocity. So minimum velocity that will be developed in the sewer is 0.45. Okay, you cannot have velocities lesser than this, otherwise silting will start. Okay, so this velocity should always be in general more than this, and this is the average velocity in a sewer. Maximum velocity you can have up to 4.5 to 5 meter per second, starting from 0.9 to 4.5 to 5 meter per second, depending on the material of the pipe or the material of the sewer. Now, we'll see certain formulas for proportionate depth, areas, velocity, and discharges. So now let us consider, see, this is a sewer. This is a circular sewer. In general, sewers are circular, okay, of diameter d. So this is diameter d. Now, this is the depth of water, depth of sewage that is flowing in the sewer, okay. So this much from here to here, it is nothing, only air. So depth is only small d. Depth of flow in the sewer is small d. So according to this depth, the sewer is flowing. Now let us assume that line, this line subtends an angle alpha at the center of the sewer. Okay. Now the depth at the partial flow. If you want to calculate this depth d, how will you find this depth? This depth will be equal to this depth from here bottom to this center. This depth minus the height of this triangle will give you this depth. So if this depth is what is this depth? That is the radius of this circle, that is d by 2. So this is d by 2 minus what is this one, this depth, height of the triangle, d by 2 cos alpha by 2. So this is alpha, entire angle is alpha. So half of this angle will be alpha by 2. So d by 2 minus d by 2 cos alpha by 2. So this gives you, if you take d common, d by d will be equal to half 1 minus cos alpha by 2. This is called as proportional depth. So now here, the small, all these letters, okay, the small d represents depth of flow for partial flow. Capital D represents depth of flow if the pipe is flowing full. Okay. Similarly, your area of cross section, if you want to find this, suppose small a. What is this small a? Small a means this much area. If you are required to find this area, this area is small a, and capital A will be entire area, that is pi by 4 d square. Okay. Now you need to find what is this area. So this is nothing but simple plain mathematics. If you know mathematics, if you know trigonometry, you can find. Nothing very rocket science about this. So this area will be pi by 4 t square into alpha by 360 degree. Okay, that means how you are finding this area? You are finding the area of this sector. This is a sector. This area of this sector minus area of this triangle will give you the area of this portion, the flowing water part. Okay, this they have done this only. Area of the sector minus area of the triangle half into base into altitude divide to cos alpha by 2 divide to sin alpha by 2. So cos alpha by 2 sin alpha by 2, 2 into this will be sin alpha by half. So this gives you pi by 4 t square alpha by 360 degree minus sin alpha by 2 pi. So this is small a, and capital A is pi by 4 d square. So small a by capital A will be equal to this alpha by 360 degree minus sin alpha by twice pi. So here you can observe, if you know the angle, what is the angle alpha, then you can find, all you need to know is to find what is the angle alpha. If you know angle alpha, you can find proportionate area, you can find proportionate depth. Now what is proportionate perimeter? P pi by d, again alpha by 360. Proportionate area means this portion, this proportionate perimeter means this portion perimeter, and entire perimeter is pi d. What is this portion? This pi d into alpha by 360. This is the formula, general formula. Thus they are finding this. Again, R equal to A by P. So what is R? Hydraulic mean depth. Uh, the proportionate area will be alpha by 360. Okay. Again, R by R, we are proportionate hydraulic mean depth. Small r by capital R. Using trigonometry, you are finding as 1 minus 360 degrees sin alpha by 2 pi alpha. Okay. Proportionate velocity will be, small velocity is 1 by n r to the power 2 by 3 s naught. Okay. Best slope. Capital V will be 1 by n r to the power 2 by 3 s naught. Okay. Now small velocity is the velocity of flow at partial. That means at depth d. Capital V is the velocity when the sphere is flowing full. So what is this small v by capital V? We are finding this is the proportionality. So this is nothing but n by n small r to the power 2 by 3 is r to the power capital R to the power 2 by 3. Slope will be same in both the cases, whether it is flowing half or whether it is flowing full, whether it is flowing partially or fully, slope will remain same. So now if n and n, both in both the cases, if your Manning's functions are equal, so v by v only will depend on r to the power 2 by 3, small r to the power 2 by 3 by capital R to the power 2 by 3. This is the case, and this already we have found this proportionate hydraulic mean depth as this. Already we have found this value. Okay, report this value. So proportional velocity will be into this value to the power 2 by 3. So small v by capital V will be equal to 1 minus 360 degrees sin alpha by twice pi alpha to the power 2 by 3. Now again using this formula, q small q equal to a into v, capital V equal to capital A into capital V. Again proportional discharge, small q by capital Q, small v a into small v by capital A into capital V. With a proportionate area into proportional velocity, you just multiply, you get proportional discharge. So in each of this formula, what we know is we can find every proportionate parameters, whether it is proportionate depth, proportionate area, proportionate parameter, proportionate hydraulic mean depth, proportionate velocity, proportionate discharge. These are the 6 parameters. Okay, you need to find. So all you need to know is only the angle subtended at the center alpha. If you know this, you can find, and if you know the formula, you can find what is the proportionate parameters. So suppose you need to find what is the proportional velocity, means you know full velocity, flow and the pipe is flowing full, you know this velocity, that is the maximum velocity. So you can find what is the partial velocity. That proportionate value, that ratio value into that this velocity will give you the small velocity value. So once this is known, we can design the sewer pipes. Designing sewer pipes is nothing but you're designing the diameter of the pipes, mainly the diameter, the depth of flow, and the gradient. So this is the pipe design is all about designing the diameter and designing the slope on which the pipe has to be laid. If it is the case of sewer, in case of water supply, you have to design the design pressure, the velocity, and the diameter, of course. So the next class we'll do solve some numerical problems based on hydraulic design so as to get a more clearer concept for this topic. And after that we'll move on to the last unit, that is your solid waste management and disaster management, and that will complete our syllabus. Thank you for listening to this video.